Can you verbalize them?
Yep. So we have stuff like f of x equals negative x cubed equals negative x cubed plus x squared plus 3x minus 3.
Okay. When you're dealing with quadratics, we can always use the quadratic formula.
Mm-hmm.
But once you get above quadratics, like cubics and quartics, there's very few easy methods you can use to find the zeros. Okay?
Okay.
This happens to be one where you can use a method they call grouping to solve this. And in order to use grouping, it requires that this coefficient divided by this coefficient be equal to the same ratio as that coefficient divided by that coefficient. And you'll notice that they are. I've got minus 1 over 1. Is that equal to 3 over negative 3? Same ratio. They're both minus 1. Okay? So, that being the case, we can, and that's the only time you can ever use this method called grouping, is if that ratio is the same.
Yeah.
Okay? So, here's how I'm going to group them. I'm going to group the x squared and the x cubed together, parentheses around it. And I'm going to group the 3x and 3 together and put parentheses around it. Now, start thinking of it as greatest common factor. What can I factor out of the first set of parentheses? What's the greatest common factor?
Just 1?
X squared.
Oh, but that's x cubed. Can we still...
Okay, a greatest common factor merely needs to be divisible into every term evenly. So if I can divide that by x squared, which I can do, and I can divide that by x squared, which I can do, then I can factor out an x squared. And I get this. What's the greatest common factor I can do on the expression in the right set of parentheses?
3.
Okay. Now, let's go back to the first thing that I factored out. Instead of factoring out an x squared, let's factor out a minus x squared. What happens is it turns that to a plus, and it turns that to a minus. So I end up with x minus 1. Whoops, hold on. Now, the next step is something that you're not used to doing. You've learned that when you're dealing with the greatest common factor, you usually only can take out one thing. But it's not true. In other words, what is the greatest common factor in that expression right there? What factor can I divide evenly into this term and this term? It's only one thing.
I'm not sure.
X minus 1.
Oh, yeah. I see that now.
So I can factor out the x minus 1, put it in parentheses, and what do I have left over?
Just 3?
Well, you got this term and you got this term. So
Oh, yeah.
3 minus x squared.
Okay.
Okay. Now, that is the factors of that polynomial. If you multiply these back together again, you will get what you started with.
Mm-hmm.
And that's the whole point. Now, the nice thing is that I started with a cubic. I pulled out a linear term, x minus 1, leaving a quadratic term. Well, you can always factor quadratic terms. Always.
Mm-hmm.
If I want to know what that 0 is, then it's plus or minus square root of 3. So my complete factoring is going to be this. X minus 1 times x minus square root of 3 times x, excuse me, I got that backwards. When I am solving that, it is 3 square root of 3 minus x and square root of 3 plus x. So here is the complete factoring of that cubic.
Mm-hmm.
Notice each one of these is a linear term. It's x to the 1, x to the 1, x to the 1. So that's usually what they want you to do with these polynomials, is split them up into as many linear factors as you can. Well, the first step was to try to figure out how to pull something out like we did, leaving a quadratic. Because know that when the other term is a quadratic, that is always solvable, even if you have to use the quadratic formula. But it's solvable. So this is the big step, is pulling out that x minus 1. And you can see that it's a little different. You're not used to doing that. In terms of a greatest common factor, you're not used to pulling out a binomial term. Usually you're pulling out monomial terms. So you kind of have to look for it. All right, what else you got? Nate? Nathan?
Oh, I'm sorry, my mic was muted. Some of them are asking how many turning points for the polynomial and to graph it and its end behavior.
Okay.
And yeah, so I want to know how to do that.
Well, give me the polynomial and I'll show you.
Okay. F of x equals x to the fourth. I don't know. That's what do I call that?
X to the 4.
Okay. Plus, actually negative x to the fourth. I'm sorry. Okay. Plus 3x to the third cubed minus x plus 1.
All right. Now, this one we cannot factor using grouping.
Yeah.
And they haven't taught you yet how to factor not using grouping. It's a lot harder. When you start using the rational factor theorem, this becomes a 25-minute problem.
Yeah.
So clearly, they don't want you to solve that. What they want you to do is graph it. And the only way you have of graphing it is on your calculator. What kind of calculator do you have, Nate?
TI Inspire.
Okay, you know how to graph this?
Yeah, I know how to put it in. I'm pretty sure that I don't need to know how to do that. But I do want to know about the end behavior and the turning points.
Okay. For me to do that, I need to graph it. So let me graph it on my grapher, and I'll bring it up on the screen.
Okay.
I use Wolfram Alpha. And let's see. You said, let's wait till it comes up. You said minus x to the fourth plus x cubed. What else?
We said minus x to the fourth plus 3x cubed.
Okay, and the cube applies only to the x, right?
Yeah, I mean, that's what it is.
That's where it's always going. What else?
Minus x plus 1.
Plus x?
Minus x plus 1.
All right. The beauty of Wolfram Alpha is it gives you exactly what you put in, so you can tell whether you made a mistake or not. And that's what we had, right? That's what we're supposed to have?
Yeah.
Okay. Now, if we look at this graph, they talk about, let's talk about end behavior first. End behavior means, what does y do as x goes to negative infinity? In other words, as x approaches negative infinity, what does y do?
Y approaches negative infinity?
Yep. As x approaches positive infinity, what does y do?
X approaches positive infinity.
Yeah.
Negative infinity for y.
Exactly. So the end behavior, the left-hand end behavior is x goes to negative infinity. Whoops. I meant put a negative sign there, sorry. And the right-hand end behavior, oh, excuse me. No, I did it right. The negative infinities are up there. Okay. So the right-hand end behavior and the left-hand end behavior is negative infinity.
Yeah.
Left-hand end behavior implies that as x goes to negative infinity. Okay. So now, what else did they want about increasing and decreasing and stuff like that?
They want how many turning points?
How many turning points? Okay. What they mean by that is where the function goes from increasing to decreasing or from decreasing to increasing. Now, clearly, and you want to start on the left, always. So, clearly, as I go in this direction, the function is increasing.
Yeah.
But the moment I get to this point, it starts to decrease.
Yeah, for a little bit.
And then it starts increasing again. And then it decreases. That's extremely important information in calculus. And that's what they're kind of doing, is they're getting you close to precalculus here.
So that's 3 turning points?
Yeah, there's 1, 2, 3. Notice that nowhere else does it turn. And in fact, if I were to look at it on a bigger scale, which is what that is, it almost looks like there's only 1 turning point. So you only see all of these turning points when you graph it close enough. But clearly you can see that it's headed down right there. All right. If you have another one, give it to me, and I'll go ahead and graph it first. And then we'll talk about turning points and endpoints.
Okay.
end behavior.
X cubed plus x squared minus 6.
Okay. Now this one, it's not as easy to see. In other words, I cannot tell unless I zoom in. If you had this on your Inspire, you could zoom in. This program, unfortunately, does not let me zoom in. If I look at this picture, it appears there's only one turning point.
Yeah.
And that would be right there, right?
Uh-huh.
No, in fact, that's not even a turning point in that picture. It's increasing the whole way. In other words, it's increasing, 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 maybe flat, still increasing.
Yeah.
So I don't necessarily see any turning points when I look at that. However, if I go back and I look at it zoomed in a little bit, the upper graph, same graph, it just shows you a little more detail, then it actually does look like it's increasing to there, and then it looks to me like it's decreasing to there, and then it looks to me like it's increasing. So I would say this one has 1, 2 turning points.
Mm-hmm.
And here's the thing. Cubics normally have 2 turning points. Quadratics are parabolas, right? Quadratics only have 1 turning point always, no matter whether it looks like that or like below. If it's a U, upside down or not, there's only 1 turning point right there. So quadratics have 1 turning point. Cubics have 2 turning points. Quartics have 3 turning points.
Yeah.
Usually. Not always. There is some cubics that only have 1 turning point, and I'll draw one. If I plot y equal x cubed, looks like this. Always increasing. There is no turning point right there. There is a point where it's equal to 0, and the tangent to that curve would have a flat slope, but I don't think that's called a turning point. So in this case here, there is no turning points. But usually, if you add anything else, an x or an x squared or any other terms, it turns that picture into this. Always. And you have a turning point there, you have a turning point there. So you usually have 2 turning points on any cubic. And that's why I feel comfortable on this particular one, that when I look at that, that is a turning point.
Yeah.
So is that.
Yeah.
Whereas it doesn't, again, show up there. Now, let's talk about the end behavior on this curve. What's the left-hand end behavior? And this one you can see it fine looking at that picture.
Yeah. Negative infinity. So x.
The left-hand end behavior, yes. As x goes to negative infinity, y goes to negative infinity.
Yeah.
In other words, y keeps going in this direction forever.
Yeah.
What's the right-hand end behavior?
Positive infinity.
Yeah, actually, is all you need to say is positive infinity. In other words, right-hand end behavior implies that x is going to positive infinity. So you don't really need to repeat that.
Yeah.
All right. What else do you have? Either like this or different.
Oh yeah, adding, multiplying, and subtracting them, polynomial.
Okay. We don't need to graph that.
Yeah, we don't.
Hold on, let me set to right. This is actually really easy. Okay, go ahead. Give me one.
I don't think I have any for this one. I just wrote it down to work with you on it.
Okay.
So if we can make one up.
I'll make one up. I'm going to take that polynomial, and I'm going to add it to this polynomial. All you do is add like terms. What do you get?
I have to minimize this to be able to see. Okay.
So your control panel was covering up your display of my numbers.
The right side, the far right side.
And you solved that by minimizing the control panel?
Yeah, well, I saw that it was covered.
Okay. Yeah, you can, that's a toggle switch. So you can always leave the go to meeting panel minimized.
Yeah, I usually do,
Okay.
but I barely got home in time from school to get started.
Okay. I was just curious. I was asking because I was curious whether it covers up the right side of your screen or not. So,
yeah, no.
Okay, so if you add like terms, what do you get as an answer?
We add like terms in both sides, so we would get okay. So I should take it one step at a time. So
do all the x cubes.
4x cubed.
Now do all the x squareds.
Minus x squared.
Oh. You got a 2x squared there minus an x squared. What is 2x minus x?
2x minus x is 1x.
Okay. Well, how many x squared you got? How many x's you got?
1.
I got a minus 4x and I got a minus 2x.
Oh, I thought you were talking about the, okay, never mind, sorry. Negative 6x.
And how many numbers?
Plus 22.
Okay. That's adding. That's really simple. We'll make it a little bit harder. Going to subtract these two. The only reason that's harder is because that subtraction needs to be applied to every term in the parentheses that follow it.
Uh-huh.
So now, how many x cubes do you have?
0.
No? You got 3 there, and you got 1 there. You're doing 3 minus 1.
2.
How many x squareds do you have?
3.
Plus, you need a sign. You can ignore the sign on the first term, but you can't ignore the sign on any of the other terms. So it's plus 3x squared. Keep going.
Minus 2x.
Good.
Minus 2.
So adding and subtracting is a piece of cake. Right?
Yeah.
Now, let's talk about multiplying. If I'm going to multiply these two, FOIL doesn't work when you're multiplying anything more than a binomial by a binomial. But what does work is every term by every term. Go over here and start on the left. multiply that by that term, and then multiply that by that term, and then multiply that by that term, multiply that by that term, go back, start there next, multiply that by that, that by that. Notice that I'm taking every term, multiplying it by every other term, and adding everything together.
Mm-hmm.
So I'm going to multiply that by that, I'm going to multiply that by that, I'm going to multiply that by that, multiply that by that. And then I'm going to do the numbers.
Okay.
And then I'm just going to combine everything. When I have 4 terms times 4 terms, I'm going to have 16 terms. And then I have to combine all like terms. So I don't want to take the time to do it with this because I didn't really mean to multiply a 4-term polynomial by another 4-term polynomial.
Mm-hmm.
But you get the idea?
Yeah, I do.
Okay. In other words, if you were going to multiply a plus b plus c times x plus y, you just do that times that, and always do it methodically. By that I mean always do it the same way. Don't do a times x and then b times x. Do a times x and then a times y. Now you're done with the a's. Now do your b's. B times x, b times y. You're done with the b's. Now c times x, c times y.
Yeah.
Add them all together.
Okay.
Now, let's talk. Did it say division also?
It doesn't say it on here, and I don't remember hearing about it, so I don't know if we'll be doing that.
Let's talk about a fairly simple one.
Okay.
How would I divide that by x minus 5? In other words, this is division. What's under the radical here is the numerator, and the divisor is x minus 5.
Okay.
And what you're going to do here is just straight long division.
Okay.
Now, the way you're going to do it is you're going to start by dividing the x into the x squared. What do you get? That's your first step always. Forget about minus 5. Forget about everything else. Just divide x into x squared.
Just x? Isn't it just x or...
Now you take that and you multiply it by both terms. So you get x squared minus 5x. Now, just like in all long division, you subtract. What do you get when you subtract?
Negative 13x.
No? You minus 7 minus a minus 5.
Negative 2x.
Okay, and now bring down the next term, which is 10, and start all over again. That's all you do, no matter how long it is. You just keep going down till you don't have a remainder anymore. So what's x into minus 2x?
What was that? Sorry, I couldn't hear.
The next step is you're going to divide that into that.
Okay, so it's just negative 2, or it's just negative 2, right?
Yep. So that goes up here. Now you take the negative 2 and you multiply it by both terms. In other words, same process, every row. You subtract, you get 0. That means there's no remainder. And it means that x minus 5 times x minus 2 equals x squared minus 7x plus 10.
Mm-hmm.
And we did it not by factoring, which is the way you would normally do it. We did it by straight long division. In other words, the problem they would have probably given you, I guess you could always do this by factoring. This is the way it would look on paper. And the way you would do it is you would take the top and you would factor it into x minus 5 times x minus 2. And then the x minus 5's cancel, and so there's your answer.
Mm-hmm.
But you can do it by long division, and that is something you have to be able to do when you get to pre-calc, is
Okay.
long division. So you need to know how to do this. In fact, they'll teach you something called synthetic division. Have you had synthetic division?
I don't think so.
Okay, not there yet. It looks like you're just kind of starting pre-calc.
Yeah.
Okay. Nathan, I have a 4 o'clock that I have to go to. So
Okay.
I will bid adieu and talk to you next time.
All right. Bye. Thank you.
You're welcome. Bye-bye.